At the forefront of coherent progress is the European Council for Nuclear Research, CERN, esteemed for its critical contributions to particle physics. As the world's most renowned particle physics research center, CERN has revealed an incredibly fascinating finding from its Large Hadron Collider, LHC, that could fundamentally change our understanding of the universe. Analysts believe these surprising revelations could uncover the presence of extraterrestrial life in a parallel reality. This groundbreaking idea has sparked excitement and intense debate among experts. Could this astonishing discovery reshape our understanding of the universe? Moreover, if confirmed, what profound insights will this discovery offer into the nature of reality itself? Join us as we delve into the recently published findings, exploring how CERN scientists are breaking their silence on this chilling new revelation with the potential to change everything we know. The European Council for Nuclear Research, also called CERN, has been renowned for its bold experiments since its inception in the 1950s. It has often been at the center of attention, sometimes for controversial reasons. Its experiments have raised concerns about the potential creation of black holes, cracks in our reality, and various other risks. One of CERN's most notable and debated achievements was the development of the Large Hadron Collider, LHC. The LHC is the world's largest particle accelerator, which began operations on September 10, 2008. It remains the latest addition to CERN's accelerator complex, spanning over 27 kilometers of superconducting magnets and a series of accelerating devices. The CERN supercollider cost more than $4.5 billion, and many argue that this money was well spent. The LHC has led to some of the most significant discoveries of recent decades, such as the discovery of the Higgs boson and various previously unknown particles. This massive machine is capable of accelerating particles around its ring until they reach near-light speeds, completing more than 11,000 laps per second. The LHC achieves this with extremely powerful electromagnets that generate magnetic fields almost 100,000 times stronger than Earth's magnetic field. Some have expressed concern about the impact of creating such strong magnetic fields on nearby devices, as well as on Earth's own magnetic field. Once these particles reach their maximum speed, they are made to collide in violent crashes, releasing enormous energy and a variety of new particles. When particles collide, a torrent of particles escapes in all directions, with most existing for only fractions of a second before vanishing. By analyzing these collisions, scientists uncover new particles amidst this chaos. Highly sensitive detectors are placed around the collision sites to record all the data. The amount of information generated is enormous, requiring immense effort to process. The LHC's experiments produce more than 15 petabytes of raw data annually, which must be carefully filtered to extract the data scientists need. By 2017, the LHC had achieved a significant milestone by permanently storing over 200 petabytes of data in its tape libraries. To put this amount of data into perspective, 1 petabyte is equivalent to around 250,000 movies. But what exactly are scientists looking for in this data? They have identified something unusual happening with a specific type of quark. Quarks are the fundamental building blocks of matter and come in various flavors, as defined by physicists. Some of these quark flavors are unstable, decaying into different particles in fractions of a second. The beauty quark, with an average lifespan of 1.2 trillionths of a second, became the center of attention due to a particular anomaly. Its decay pattern differed from what researchers expected based on the standard model. According to predictions, when a beauty quark decays, it is influenced by the weak force and transforms into lighter particles known as leptons, either an electron or a muon, with the standard model predicting a 50-50 probability for each particle. However, LHC data revealed that these quarks decayed into muons 70% of the time instead of electrons. This discrepancy suggests the involvement of a previously unknown type of particle in the process. Some researchers speculate that a new type of physics might be at play. A new force-carrying particle would imply entirely new physics, potentially expanding the standard model and answering many unresolved questions. The possibility of new physics challenges the standard model, which is our best framework for understanding how particles behave. The standard model describes three fundamental forces: electromagnetic, strong, and weak interactions, but it does not account for gravity or dark matter, the universe's most dominant form of matter. In recent experiments, scientists found an anomaly in their data that deviated from the standard model's predictions. While such deviations are not uncommon given the LHC's massive data output, this particular observation intrigued researchers enough to warrant further investigation. Could this new force be explained by the presence of another fundamental particle, referred to as Z prime? This force-carrying particle, although highly speculative, has not been detected so far. Researchers believe it may interact uniquely with electrons and muons, but the extent of its interactions with standard model particles remains unclear. If scientists confirm the discovery of a new force-carrying particle, it would mark a long-awaited breakthrough in physics, unraveling age-old mysteries of the universe and addressing unsolved problems, such as the nature of dark matter and the role of the Higgs boson. Some experts believe this hidden force could help achieve one of physics' most ambitious goals, unifying the fundamental forces of existence. According to Elon Musk, CERN built the largest and most powerful particle collider in human history, the Large Hadron Collider, LHC, between 1998 and 2008. More than 10,000 scientists from various institutions and laboratories across over 100 countries contributed to this effort. It lies within a 27-kilometer-long tunnel on the border between France and Switzerland, near Geneva, about 175 meters underground. The first collision recorded at the LHC had an energy of 3.5 tera-electron-volts, TeV, per beam, vastly exceeding the previous world record. Following upgrades, the energy reached 6.5 TeV per beam. Musk noted that the LHC excels at proton beam collisions and can also accelerate lead-ion beams. Proton and lead collisions are typically conducted for 1 month, allowing scientists to test predictions of various particle physics theories. The primary goal of the LHC is to study the properties of the Higgs boson and search for the vast array of new particles predicted by subatomic physics theories. Hadrons, which include protons and neutrons, are composite particles made of quarks held together by the strong force, akin to how electrons and atoms are held together by electromagnetic forces. The LHC brings two colliding particle beams together to interact. The Higgs boson is believed to be a fundamental particle associated with the Higgs field, the quantum excitation of which resembles waves in the ocean. Discovered at the LHC, the Higgs boson was a groundbreaking achievement announced on July 4, 2012, by CERN. Following its discovery, research into this elusive particle has continued. During the LHC's third cycle, further upgrades are planned, culminating in 2029 with the completion of the high-luminosity LHC. This upgrade will enable CERN to conduct more collisions, producing a significantly higher number of Higgs bosons annually, which may provide critical insights into physics beyond the Standard Model. This increased production of Higgs bosons will open up new opportunities for researchers to investigate rare and unusual phenomena, including those that do not align with the Standard Model of physics. By analyzing these additional Higgs bosons, scientists hope to identify unique interactions or decay processes that could point to undiscovered particles or forces. One of the primary goals of this ongoing research is to gain a deeper understanding of dark matter, an elusive and mysterious form of matter that makes up approximately 27% of the universe but remains undetectable by conventional methods. Dark matter does not emit, absorb, or reflect light, making it invisible to telescopes. However, its presence can be inferred through its gravitational effects on visible matter, such as galaxies and stars. If the LHC experiments reveal particles that interact with dark matter or provide clues about its composition, it could revolutionize our understanding of the cosmos. Another area of focus is the Higgs boson's role in the early universe. Scientists theorize that the Higgs field, which gives particles their mass, played a crucial part in the evolution of the universe immediately after the Big Bang. By studying the Higgs boson's properties in detail, researchers aim to uncover how the universe transitioned from a chaotic, high-energy state to the structured cosmos we observe today. Additionally, some researchers are investigating the possibility of alternate dimensions or parallel universes. Theoretical frameworks, such as string theory, suggest that multiple dimensions beyond the familiar three of space and one of time could exist. If the LHC's experiments detect anomalies that align with these theories, it could provide the first tangible evidence of higher dimensions. For instance, certain particles might leak into these dimensions, creating patterns in the data that deviate from standard model predictions. The implications of such discoveries extend far beyond the realm of physics. Understanding the fundamental forces and particles that govern the universe could pave the way for new technologies and applications, much like how quantum mechanics gave rise to modern electronics and computing. From advancements in energy production to revolutionary medical imaging techniques, the potential benefits are vast. However, these experiments are not without their critics. Some argue that the immense resources allocated to CERN's projects could be better spent addressing immediate global challenges, such as climate change or poverty. Others raise ethical concerns about the risks associated with high-energy collisions, fearing unintended consequences like the creation of miniature black holes or disruptions to Earth's magnetic field. While these scenarios are deemed highly unlikely by the scientific community, they continue to fuel public debate. Despite the controversies, CERN remains committed to pushing the boundaries of human knowledge. Its scientists emphasize the importance of fundamental research in driving long-term progress and innovation. As the LHC continues its operations and prepares for future upgrades, the world watches with anticipation, eager to see what secrets the universe may yet reveal. As CERN continues its groundbreaking experiments, researchers are also addressing some of the biggest unanswered questions in particle physics, including the nature of antimatter. Antimatter, the counterpart to ordinary matter, should have been produced in equal amounts during the Big Bang. Yet, for reasons still unknown, the universe contains significantly more matter than antimatter. This imbalance has puzzled physicists for decades. By studying particle collisions in the LHC, scientists aim to uncover asymmetries in the behavior of matter and antimatter that could explain this mystery. Another intriguing focus is the possibility of discovering supersymmetry, a theoretical framework that extends the Standard Model. Supersymmetry posits that every known particle has a heavier, undiscovered partner particle, or superpartner. These superpartners could explain the composition of dark matter and help unify the fundamental forces of nature. While the LHC has yet to detect any evidence of supersymmetric particles, the search continues, fueled by hope that higher energy collisions or refined data analysis might reveal their existence. CERN is also exploring the potential of quantum gravity. Unlike the electromagnetic, strong, and weak forces, gravity is not currently integrated into the Standard Model. Theories like string theory propose that gravity arises from the interaction of hypothetical particles called gravitons, which might only become detectable at extremely high energies. If the LHC experiments were to uncover evidence of gravitons or quantum gravity effects, it would bridge the gap between quantum mechanics and Einstein's theory of general relativity, creating a unified framework for understanding the universe. The upcoming high-luminosity LHC upgrade, scheduled for completion by 2029, is expected to significantly enhance CERN's ability to conduct these investigations. By producing more collisions and collecting greater amounts of data, scientists will have a higher probability of observing rare phenomena that could lead to transformative discoveries. This upgrade will also enable CERN to test theories with unprecedented precision, providing clearer insights into the fundamental laws of physics. Beyond particle physics, CERN has also contributed to technological innovation in numerous fields. For example, the World Wide Web was invented at CERN in 1989 by Tim Berners-Lee as a way for scientists to share information more efficiently. Advances in accelerator technology have also found applications in medicine, particularly in cancer treatment through proton therapy, which uses particle beams to target tumors with high precision. These contributions demonstrate how fundamental research can yield practical benefits for society. CERN's work has inspired collaborations worldwide, with scientists from over 100 countries contributing to its projects. These international partnerships highlight the unifying power of science in addressing universal questions that transcend borders. As CERN continues to push the boundaries of human knowledge, its discoveries have the potential to reshape our understanding of the cosmos, inspire new generations of scientists, and unlock technologies that could transform the future. With the LHC poised to uncover new realms of physics, the next decade promises to be one of the most exciting periods in the history of science. The mysteries of dark matter, antimatter, supersymmetry, and quantum gravity remain challenges for humanity to solve, but as CERN advances, we edge closer to answers that could redefine our place in the universe.